Traditionally, one of the great goals of electronic structure calculations on molecules is to determine their equilibrium geometry. Now, in the case of diatomic molecules, this is relatively straightforward, and you'll recall that if we were to vary the distance between the two atoms in a diatomic, we should see, at least in the ground state, a variation that would look something like this, where the curve goes down as the two atoms come together. It reaches a minimum, which is the equilibrium geometry, or in this case, the equilibrium bond distance. And then it rapidly increases again as the two atoms get closer together and goes up to approaches infinity. Okay, but here we're only varying one coordinate, and so we can just simply repeat the electronic structure calculation at several different coordinates and ultimately determine what the geometry of that molecule might be. Now, what does this look like when we're talking about a polyatomic molecule? Well, clearly in a polyatomic we have more than one vibrational coordinate, and so defining the potential energy surface, as we've done here for a diatomic, is going to involve a bit more work. Now, just to give you an idea, let me redraw a picture that looks sort of like this, but we're now talking about a polyatomic. Now, instead of having a two-dimensional curve that represents the potential is going to have some number of dimensions relative to the number of vibrational coordinates. So if, for example, there were two vibrations, and this actually isn't a real molecule, but let's suppose there are two vibrations, we might add a third dimension. So I'm trying to indicate in this that we're looking at a bowl, if you will, into which the molecule can fall and achieve an equilibrium configuration that now represents more than one coordinate. So, if you will, the coordinate system might be drawn here on the bottom as two coordinates. I'll call them R2 and R1. And so we need to minimize both of those coordinates in order to find an equilibrium geometry for the polyatomic. All right, now this process can be automated within electronic structure programs, and one of the key mathematical relationships that allow it to happen is something called the Hellman-Fineman Theorem. And we're not going to talk in detail about the Hellman-Feynman theorem, but let me at least tell you what it is about. If we want to find the minimum of a potential surface, we can calculate for any given pair, any given coordinates, that is of the nuclei, what the energy is, what the electronic energy is at that point. All right, so this basically tells us what is the electronic energy at the point R1, R2 in this particular example. All right, in order to get down here, we need to have some way of finding our way down the slope to get to this minimum. So in other words, we need to know what the slope is there so that we know how steep the slope is, that is, how close are we to falling into that hole. But then we can use that to model our calculation at several different points. And when we get down to a point where the slope is 0, then we know we've achieved the minimum. All right, the slope here is, in effect, it is dE dr1 and dE dr2. All right, so these are the slopes that we would need in this particular case to do that. Well, the Hellman-Feynman theorem gives us a way of calculating what those slopes are if we are in an orbital that represents an eigenfunction of the Hamiltonian. Okay, for example, if I want to know what the slope of the energy is with respect to some parameter, and the Hamiltonian depends upon that parameter, remember the electronic Hamiltonian does depend upon the nuclear coordinates, then it turns out that I can evaluate this, for some eigenstate, as the derivative of the Hamiltonian with respect to that parameter. All right, so when I'm on one of these surfaces, when I'm at a point here, I am effectively at one of these eigenstates. So if I can express what the derivative of the Hamiltonian is with respect to a given parameter, or in this case, a coordinate, so this could be R1 or R2, then I can determine what the slope of the energy is at that point, and then that allows me a way to slide down this surface until I get down here to the minimum. So this is in effect how these electronic structure programs find the equilibrium geometry for a given molecule. Now, you don't have to worry about the details of these mechanics because this is all programmed into these codes like Gaussian or Spartan. But I do want you to understand that that's what these codes are doing. So when you ask it to optimize geometry, essentially what it's doing is it's carrying out a process where it may start at some point. This may be the point at which you input the geometry of the molecule, and it's going to use this relationship to determine the slope at that point with respect to the coordinates and ultimately find its way to the bottom. Now, the algorithm is a little bit more complicated than that, but that's the essence of it. Now, one thing that you need to be aware of is that some surfaces, some polyatomics actually have a fairly complicated potential energy surface, and they may have more than one position that is a local minimum. For example, if I were just drawing this in one, in a two-dimensional case, I might have a surface that looks like this. Okay, very complicated with several local minima that are potentially places where I might get stuck and find that the slope at these positions was equal to 0. Now, in many molecules, this may be a minimum in some coordinates, but not in all coordinates. However, these local minima are not the equilibrium geometry of the molecule. They just represent places where there is a stable point, where the molecule can exist in those positions, in those shapes, if you will, but they can ultimately be dislodged and go down to a global minimum, which is the potential energy surface minimum. And the global minimum is the one that represents the equilibrium geometry of the molecule. All right, so when we're talking about vibrations and these coordinates, it's useful to know how many degrees of freedom we're talking about. So I'll note that this derives from the number of nuclear degrees of freedom in a molecule. So for example, if I have n atoms in a molecule, then I'm going to have a total of 3n degrees of freedom. Why is that 3n? Because there are 3 dimensions. And so each atom has an x, y, and z coordinate, and all of those coordinates represent degrees of freedom. Now, from this, I can eliminate 3 of these that are basically due to translation of the molecule. So these are essentially the molecule just moving around in space, so it is motion of the center of mass of the molecule. And that doesn't really impact any of these things because the molecule's properties don't care about where it is in space. Another 3 of these are going to be related to rotation. And again, this is, as you rotate a molecule, it doesn't change the force field that the electrons feel. It doesn't change the force field that the nuclei feel. It just changes the orientation of the molecule in space. So these can be eliminated, and what's left are the 3n minus 6 degrees of freedom that represent vibration. And so these are the ones that ultimately need to be optimized in order to find a global minimum for a potential energy surface. Now, how do electronic structure programs do with this? Well, let me give you a few results so you can see, how this basically stacks up. And this is going to be for fairly simple molecules, single center molecules, but it gives you at least a rough idea of how reliable the results are from these calculations. Now, what I'm going to do is differentiate this by the basis set that's used for the electronic structure calculation. So if you'll recall, in the previous lesson we talked about these basis sets. STO3G is using 3 Gaussians to represent a Slater type orbital for each of the orbitals used in the basis set. All right, we could also have 321G, which is a split basis. 3 orbitals used to represent the core orbitals of the atom, 2 represent a tighter set of valence orbitals, and 1 to represent a loose set of valence orbitals. We also could have 631G star, which is a little bit larger version of this 321G, but it also includes polarization. That's what the star means. And finally, we'll compare this with 631G star, in which we've added polarization to both the p orbitals and the s orbitals. So these are the various basis sets that we're going to scan across. And what I'm going to do is simply, in terms of bond length and bond angle, give you a range of the sort of errors that we see in the geometries that we get from these calculations. Well, for STO3G, bond lengths tend to be within 2 to 5% of the actual values. So they're reasonably accurate. You're going to get a pretty good rough idea of the bond lengths of the molecule. The bond angles are a little bit better. They're usually between 1 and 4%. For 321G, interestingly, this goes down to about 1%, while the bond angles get a little worse at 3 to 5%. All right, so you can see that these different basis sets have different strengths, if you will, when describing these molecular geometries. For 631G star, we go to about 1 to 2.5%, so it's a little bit more accurate than the STO3G, but not quite as accurate necessarily as the 321G. I don't understand that, but that was what the data I looked at seemed to indicate. For the bond angles, however, the 631G star does a much better job than the 321G. Finally, for the 631G star, so we're adding polarization functions. This is essentially the gold star of these calculations, so we can think of this as being like the Hartree-Fock limit. And we find that bond lengths typically are between 1 to 1.5% in error, whereas bond angles still about 1 to 2%. So it looks like this is essentially, from a Hartree-Fock calculation, this is what you're going to get, and I have to say this is a pretty good margin for error. These are time-consuming calculations, and as molecules get larger, these are going to be harder and harder to do by more sophisticated basis sets. So this is about what we're going to get from most electronic structure calculations. Now, I should mention that there is another approach that one can take for these. It is not any more accurate than this, but it is a little bit easier to implement. And it's a calculational procedure called molecular mechanics. And so I'll write that down. And these have been developed over the last, I'll say 30 to 40 years by a number of people. But essentially what the whole idea is that we're going to represent the potential surface on which the nuclei move as a mathematical function. So it's basically using math functions to represent V of R. Now it does this in a piecemeal way. It may have one mathematical function that will represent a carbon-hydrogen stretching force. It may have a different potential that would represent a carbon-oxygen stretching force, and so forth. So there are many different mathematical functions that are used, as with many different sets of parameters, and that's how these things can be actually reasonably accurate in terms of predicting geometry. What they do is they fit the parameters in all of these functions so that they best match observed data. All right, so these are not just sort of random functions that we're going to use in these molecular mechanics approaches, but we're using them to fit data that we observe experimentally. All right, and then finally, we would apply different algorithms to find the functional minimum. So in the same way that we go through this process for an electronic structure calculation, we would apply a minimization algorithm. And that minimization algorithm will help us determine what the equilibrium geometry would be for these molecular mechanics potentials. And as I mentioned, the result that you get from this is actually about as accurate as the results that you get up here from Hartree-Fock self-consistent field calculation. However, it's important to realize that these are developed based on observed data. So if you have a new molecule that has some sort of exotic electronic structure, the molecular mechanics potentials may not be a good fit for what you're trying to do. But they nevertheless, for the vast majority of closed shell molecules, represent a great way to get a very quick read on an equilibrium geometry for a molecule. And for example, if you go to the MoldU site, most of the time when you see a geometry for a molecule in that site, it is representing a molecular mechanics geometry, not an electronic structure geometry.